Thank you very much to organizers for the opportunity to speak. My talk will be about holographic correspondence, prominent method to study non-perturbative physics in four-dimensional gauge theory. Today we'll discuss a simple case, a toy model, holographic description of four-dimensional Maxwell theory, the same Maxwell theory which already was mentioned and studied in the talks by Alex and Maria. Let's start with a reminder how we usually formulate holographic correspondence. And the definition which I will use, it's not the only possible definition, but it's a convenient definition for my case because I will be able to play with it, is that if I have a theory on the boundary and I calculate the partition function of that theory on the boundary, then there is also a theory in the bulk which lives in a one-dimension higher manifold, which has a boundary, and that's where the boundary is. And if I calculate the partition function of that bulk manifold, the result of those two calculations, the partition function on both sides will be the same. The theory in the bulk is gravitational, and therefore, besides integrating local degrees of freedom, I have to include all possible topologies. And we know that this is the case in the conventional holography. We know that from, let's say, Hawking-Page transition, which describes field theory, four-dimensional field theory at finite temperature. So I explicitly put here a sum over topologies. Also, in principle, if your theory is gravitational, you can think that this sum is already included in the integral over local degrees of freedom. Okay, so more recently, people realized that if you want to include all possible topologies, there will be wormhole topologies, and with those topologies, interpretation in terms of a particular boundary CFT might not be possible. I will not discuss the scenario that it is still possible. I will discuss the scenario that it is not possible, and that in the boundary, what you have instead of a particular theory, an ensemble of theories, and therefore you equate the path integral in the bulk to the average over ensemble, to average over a boundary probabilistic ensemble. So basically you have different theories and you weight them with positive real coefficients and calculate the partition function that way. And we know that there are examples where this is how holography works. One famous example is the duality between GT gravity in 2 dimensions and one-dimensional matrix model. There, the ensemble is very, very clear. And there are also examples of 2-dimensional ensembles, dual to 3-dimensional theories. And perhaps the earliest and most famous one, but not quite working example, is a work by Mellon and Witten from 2007, where they tried to calculate the partition function of pure 3-dimensional gravity. They had to sum they had to calculate this path integral by summing over all possible 3-dimensional solid tori. And they calculated the sum, but unfortunately, the result was not unitary. It was not possible to map it to an ensemble of any 2-dimensional CFTs. So there was some problem with this proposal. But more recently, Mellon and Witten had a more successful proposal, and besides them, there was a parallel work by the Cornell group, where the ensemble is very well defined. It's an ensemble of all possible Narayan theories, and Narayan theories are free scalars in 2 dimensions. You can think of a compact scalar. And if you average over the whole moduli space, it's a continuous moduli space. If you average over a moduli space with a canonical measure, then the result is actually given on a boundary side by something meaningful. Mathematically, it's given by this sum. And this sum can be understood, can be interpreted as a sum over all possible 3-dimensional solid tori. And then you can ask, what are the local degrees of freedom? Local degrees of freedom are given by the U1 Chern-Simons theory. So the story is that you have 3-dimensional Chern-Simons theory. It's a topological theory. You can put it on any 3-dimensional manifold, and then you can calculate a partition function on any 3-dimensional manifold with a boundary. And that would be a result. That would be the conventional Chern-Simons theory. But what this proposal suggests is that you actually need to sum this path integral. You can need to additionally sum it over all possible 3-dimensional geometries. In this particular case, somehow only solid tori are necessary to include. So this is a working proposal. Now, if we reflect on this and we say, okay, there is a 1-dimensional example, 2-dimensional example, what about high-dimensional examples? There are no examples so far. And many people say that this ensemble story, it's a genuine story, it's a genuine interpretation of holography because of the wormholes, but it's only for lower dimensions. And if we go into higher dimensions and we have something like a duality between unequal force superior Mills and type 2D string theory, there will be no ensemble. So to try to understand that, I want to discuss higher dimensional case, and I will try to discuss the case of four-dimensional Maxwell theory today.
But we also know that sometimes it's not true. There are examples where it's not true. But
What are the examples?
UND5 theory.
I'm not very familiar. We'll not be able to comment on this. We can discuss later what breaks down. You mean it's not true that you don't need to have an ensemble, just one theory is sufficient?
Just one theory.
Oh, that would be. There are plenty of examples like that, even in my talk. It's possible to have this one theory in this kind of setup, but there will be just one particular example in a zoo of many examples with an ensemble. Okay, so so second slide, I want to tell you a little bit more about this framework which we are trying to develop to understand these examples better. So some time ago, we realized that maybe it's worth generalizing those two examples on the previous page and basically start with arbitrary three-dimensional topological field theory. And you can always think about three-dimensional Chern-Simons theory. And we, in principle, understand how that works. You can calculate path integral of a three-dimensional Chern-Simons on any manifold with a boundary. And what you usually get is a conformal block of a rational conformal field theory. That's a standard result which goes back to Witten's 1989 paper. Okay, but then if it would be a conformal block, that would not be a partition function of any particular CFT. So that's not what we want to do. We want to start with a three-dimensional field theory, like Chern-Simons. We want to sum it over all possible topologies. I will tell you later how to do it, but let's sum it over all possible topologies. Our proposal would be that it is due to an ensemble of boundary theories, and we formulated what kind of theories can emerge on the boundary. And intuitively, if you're working with 3D Chern-Simons, the theories which can emerge on the boundary are theories which are made out of conformal blocks. All possible field theories, CFTs, which are made out of conformal blocks, which you calculate in a dual 3D Chern-Simons. Okay, but this is still a vague proposal at this point because I didn't tell you how to sum over topologies. This is not a trivial question. And if you look at this, all the proposals, people would just sum over tori, solid tori, or mathematically they would sum over a mapping class group of a torus. And that is certainly a good starting point, but it's very clear based on 2007 paper of Mellon and Witten, where they try to quantize pure gravity, that this is not sufficient. So our recipe is to sum over mapping class group, but you need to add one very important crucial element. You also need to add genus reduction. So instead of working with a boundary torus, you need to start with a Riemann surface of a very large genus and sum over mapping class group over that surface. That's a well-defined group. And then after that, do the genus reduction. And in the limiting procedure where you start with an infinitely large genus, there is a mathematical theorem based on understanding of three-dimensional manifolds that in this way you will cover all possible three-dimensional manifolds with a given boundary. And therefore, I can be confident that in this way you will sum over all three-dimensional manifolds. And moreover, I will tell you what kind of weight you need to assign to every single manifold. So in principle, this becomes a computationally complicated but very concrete proposal. We were able to show about a year ago that if you sum any TQFT on all three-dimensional manifolds, the result can be written as a sum of boundary partition functions, and all the coefficients are positive. So we have shown that this proposal actually leads to a unitary ensemble on the boundary because all coefficients are positive. And as another sign that we are on the right track, a very recent progress by a graduate student in our program, Ahmed Barbar, who was working on this from the very beginning. He realized that this formula we had for those coefficients, it was giving you that those coefficients are manifestly positive, but also the formula was very complicated because you had to calculate something on an infinite genus. So that's something very abstract, manifestly positive, but abstract. Very recently, he realized that those coefficients actually equal to the size, they're related to the size of the group of symmetries of a particular CFT. And if you're familiar with something like Siegel-Weil formula, then you know that these coefficients, they smell right. These are the right coefficients which appear in mathematical formulas of this kind. And the whole fact that this is just a characterization of a CFT has no relation to genus. That, I think, is a litmus test that we are up to something tangible and correct. Okay, I do not know how much time I have spent, 10 minutes. So I want to tell you what kind of examples we have. There are plenty of examples now. One can interpret early works, not our works, but just early works. One can interpret this early works in this framework. You can work either with the minimal models, you can work with the Zemina-Witten models. We so far mostly work with the abelian Chern-Simons, and we considered we summed abelian Chern-Simons over all possible topologies. I have shown that it's dual to finite ensembles of Narayan CFTs, and there are some technical progress understanding how it works in different limits and all possible and on the manifolds on Riemann surfaces of all possible genera. So there is a lot of mathematical understanding how the abelian story goes. And then also, if we have this framework, we can go back to pure gravity in 3D, and we can ask if we can fix that problem there, non-unitarity. And conceptually, we should be able to, if we can start calculating things for very large genus. But mathematically, there is an issue that the spectrum of the TQFT, the resonant TQFT, is continuous. And this looks like a conceptual challenge rather than a technical challenge, because all the calculations, they not only become intractable, they're also ill-defined because of the divergences. So there's probably some issue, conceptual issue, how to make a jump to pure gravity, and that would require regularization. But anyway, going back to the topic of my talk today, I want to apply this framework to high-dimensional examples. Okay, so my example is very simple. It's a Maxwell theory, four-dimensional Maxwell theory. I will tell you the answer right away. The theory which you need to sum over topologies is this DF type theory. It has two forms, D and C. And this is a simple action, and N is an integer number called the level. And some people recognize this as a topological sector of type 2B supergravity, which in ADS5. So there's and another probably intersecting group of people will also recognize this as a symmetry TFT of Maxwell theory. So just the idea that we are working with this topological field theory, there is nothing new about it. That's a usual suspect in this context. And then you can try to do the following. You can start with the Maxwell theory. Maxwell theory has been already discussed today, so it's I don't need to repeat. It's a theory of one gauge field, and it's parameterized by the complex coupling constant tau. And the coupling constant tau lives inside the fundamental domain because there's SL2Z symmetry. And I will be always considering Maxwell theory placed on a spin 4 manifold. On a spin 4 manifold, if I put it on a more complicated manifold, there will be subtleties, which are also discussed in the literature. I don't want to discuss them today. I will put them on a spin manifold. There is a full SL2Z symmetry. And the only interesting thing I can do in this case, I will consider a manifold with non-trivial 2 cycles. Because if my manifold is S4 or S1 cross S3, in proper sense, the partition function is trivial. There is a determinant of small modes, but there are no non-trivial modes because U1 gauge field cannot wind anything, and therefore it's trivial. I will consider a 4 manifold which has 2 cycles. So let's say I will be considering S2 cross S2. If I do that, then I can couple my gauge field to external 2 forms. So W2 are bases of 2 cohomologies, and I split them into self-dual and anti-self-dual, and zeta and zeta bar are 2 independent classical fields. These are classical background to which I couple my Maxwell theory. Okay, so what I can do now, I can calculate the partition function of this theory. It was calculated in 1995 by Witten and by Berlinde, and Berlinde realized that this partition function is basically equal to the path integral of this topological field theory on a manifold which will end on this four-dimensional manifold, which will have this four-dimensional manifold as a boundary. Okay, and basically it was 2 years before the holography was invented, but the result was there that if you start with this theory, level 1, it's very important at level 1, then you will match the partition function of this four-dimensional theory and this five-dimensional theory. If the theory has level 1, it's what is called topologically trivial, which means that it doesn't matter what kind of five manifold you consider, you will always get the same partition function. And therefore, the issue of topologies cannot appear in this case. There is no issue of ensemble, going back to Liam's question. There is only one theory in the ball. There is only one theory in the boundary. There is no issue of topologies because any topology will give you exactly the same result. We want to sum over topologies that will literally renormalize the amplitude of your wave function, but it cannot change the wave function. A question?
Well, just a semantic comment, people constantly will call this however, they call it boundary.
Well, I understand that, but I think this would apply to three-dimensional consignment dual block. This is a similar
It's a
data.
much older thing than it is here.
I think
Much less mysterious. Not the large and duality.
I agree, but what I'm trying to do is conceptually different because I'm not trying to relate path integrals with the bulk conformal blocks. Actually, I'm trying to relate that to partition function. So in case of a trivial theory in the bulk, there is essentially one conformal block, and therefore related to partition function. But as soon as I take n to be larger than 1, your issue will be present because if I try to calculate, let's say I take n to be larger than 1. Try to calculate this path integral of this theory on a four-dimensional, on a five-dimensional manifold. There will be different results depending on how I put boundary conditions for the other part of the five-dimensional manifold. That will have different conformal blocks. That's not holography. This is this is not holography. I don't call it holography. I specify. I accept this is not holography.
It's just something that I thought.
All right. Peter, you're asking exactly the question which you want to emphasize and how my proposal, our proposal, is different from the bulk boundary correspondence. Well, I think this is an excellent question because if I don't convey that, everything else is pointless. The conventional bulk boundary correspondence or the same issue exists in TQFT, which is very similar, because when you have a four-dimensional manifold multiplied by an interval, or in case of three-dimensional topological proof where you have a boundary, a two-dimensional thing multiplied by an interval, so you have something like a cylinder with two boundaries, and of course you can put boundary conditions here and put and get a particular wave function on this boundary, but it depends on what kind of boundary conditions you put here. And you can choose particular boundary conditions here to get a full partition function, but this is still bulk boundary correspondence because you're putting by hand at this end what you want. I'm not discussing that. That's not my proposal. My proposal is different in the following way. You'll have a five or three-dimensional manifold with only one boundary. Okay, just five. Cap it so there's no other boundary. And if you just calculate a path integral, it's not a large n. This criticism is accepted. It's not large n.
These people were doing these things long before, what we call this.
But not the things, but not the things I'm doing.
Yeah, the different is here.
Right, so I want to emphasize what is different in our proposal. Let's consider something like ADS5. Then you can calculate the path integral of the topological theory over ADS5. It will be a particular combination of conformal blocks. It will not be a partition function of any theory. It will not be invariant of the modular transformation. It will be a particular combination of conformal blocks. That's it. The proposal we have is that if you add to ADS5 all other possible topologies and sum them up, then you will get something. First of all, by construction, you'll get something modular invariant. And second thing, we tell you that this combination of the conformal blocks actually will be a linear combination of CFT partition functions with positive partition.
But it doesn't have to be ADS, where the things that.
Well, if you're saying that the word ADS meaningless because the bulk is topological, that is accepted. So it's ADS only in terms of the topology, and we are summing over bulk topologies, not bulk geometry. We more accurately, I should say, let's say in 3D that I'm summing over solid tori or other things. It's not a thermal ADS, it's not the human geometry, because metrics is only present at the bound. That criticism is valid, it is accepted, and how to bridge this thing without genuine metric to the thing with the genuine metric is an open question.
So from Maxwell's side, you have dependency out and from even theory, it appears a boundary condition. That's the top it appears boundary condition.
Yeah, now there is no tau in this theory. There is no tau in this theory. It will appear only at the boundary of this 5-dimensional space. You have to introduce it. It's only there because tau knows about metric, and that is only present in the bound. So, okay, so now I can explain our proposal. I think my time is running short, so I will try to explain the proposal. If you take this theory and take n larger than 1, then, as I said, for any given topology, for any given 5-dimensional geometry, you will not get anything meaningful. But if you carefully sum over all of them, you will have a result, which is an ensemble. It's an ensemble of n plus 1. Let's take n to be prime just for simplicity. It will be an ensemble of n plus 1 different Maxwell theories with different coupling constants. Okay, to see it more clearly, I have a slide how to quantize this theory. You need to add a term exactly at the boundary, and you need to do the quantization, which is an analog of a holomorphic quantization of 3D Chern-Simons. I will not go into detail, but there is a holomorphic scheme of quantizing 3D Chern-Simons. You can extend it to 5D, and actually the idea how to do that already was present in the Berlin's paper. And you can calculate all possible conformal blocks, but the resulting identity, which is a non-trivial identity, looks like this. You have the path integral over 5-dimensional manifolds. You have to sum over all of them. Don't ask me why these are all of them, because in 5D, I cannot really argue rigorously that you cover all of them, because 5-dimensional topology is much more complicated than 3-dimensional topology. And you sum in a particular way over mapping class group. And in case when n is prime, you don't have to worry about genus reduction, you just continue summing. And this sum will be proportional. The overall coefficient should be renormalized, but it will be proportional or equal if you wish after renormalization to a sum over n plus 1 distinct Maxwell theories, which are different by the values of the coupling constant. Okay, and why those particular values of the coupling constant appear? 1 minute. That could be understood. Actually, it could be understood from the gauging. One can understand that all of these n plus 1 different Maxwell theories are actually orbifals of the same Maxwell theory, and that is a reference to Alex's talk. One can make a connection there. Okay, few words. Can we understand anything about n equal 4 super young males? Unfortunately, I don't have an answer what will happen with n equal 4 super young males. But some people believe that supergravity or quantum gravity field, or the string theory, is actually a topological field theory in appropriate sense. I cannot really expand this thought because there are many gaps in my understanding. I think the whole community doesn't understand many things, but there is a certain way to think about quantum gravity that this is a topological field. But really, to make the connection between this proposal, which is a toy model proposal with TQFT, and the models with genuine graviton in the bulk, I think for that, we need to understand how to solve pure gravity in 3 dimensions. I think that will be the most natural place to attack. And as a spin-off, there is also a comment about n equal 4 super young males being due to expected string theory in EDS 5 versus 5. There was a question going long ago whether the boundary theory has FUN gauge group or UN gauge group. And the answer is that if you look carefully at what happens in the bulk, there are actually 2 ways to quantize bulk fields. And this BC fields, you can have 2 different families of boundary conditions. You can have what is called real quantization when one of the fields is zero, we're gonna have holomorphic quantization, which I briefly mentioned in my talk. And depending on what kind of boundary condition we impose, we will have either SUM or UM theory. Okay, I'm ready to conclude. So I want to tell you that there is a new framework which incorporates all known 2D/3D examples of ensemble holography. Maybe it also includes 1D, 2D examples. That still has to be understood. One thing I wanted to tell you is that this framework includes four-dimensional examples. Maxwell theory is a pre-theory. You can say it's a toy example. I agree with that. But since you have at least one example, it's possible that other examples will follow. And therefore, it's an interesting question to understand how this framework for holography is related to the conventional framework. And probably the right way to attack is to understand how semi-classical gravity emerges in 3 dimensions. And just to make the very last comment, which I didn't touch during my talk at all, is that algebraically, with the way how this different ensemble of theories emerges, you can understand that through the connection with classical and quantum codes, which are present always when you have an abelian symmetry. But this is sort of this is a tangential, but nevertheless an interesting remark which I wanted to make. Thank you.
So normally in holography, you can match deformation.
Yeah.
In a Maxwell example, can you say only the holographic removal of that angle up to further? Like normalizing like that.
Yeah, so this is a good question, whether you can do all of the information. Any, I understand. We can do any deformation. So there is another more rigorous formulation of holography, which creates the Hilbert space of the boundary and the Hilbert space of the ball. Therefore, you can do an operator which couples to any arbitrarily in the Hilbert space on both sides. This kind of holography, as you can see, we are not matching Hilbert spaces. We are basically splitting. Let's think about two-dimensional conformal field theories. A Hilbert space, the sum over Hilbert space is a partition function. But you can resummon in the groups and hold that group to conformal block. So what happens here is that the bulk theory only knows about conformal blocks. So it factorizes the Hilbert space into not entirely subspaces, but something like strata. I don't want to be very mathematical because I'm not sure what's the right way to think about it. And essentially, the only thing which you can do in the bulk is to have an operator which respects that structure. So in case of abelian Chern-Simons or in case of DC theory, you can couple to things which respect, let's say, chiral algebra. So you can introduce this classical backgrounds which are wrapped into cycles. The zeta and zeta bar, there's a classical backgrounds, there's a classical external backgrounds in terms of the four-dimensional Maxwell, and there's a boundary conditions for the bulk field. And that's this is a conventional holographic dictionary when the boundary value of the bulk field are coupling constants on the bound. That is satisfied. And you can also discuss local operators made out of a field. But you cannot do a general deformation. You cannot add a mass to the photon or something.
Sorry, so I missed in your 40 example, what is the ensemble of boundary theories?
Yeah. The ensemble of boundary theories in this case, these are all Maxwell theories with different coupling constants. And the formula for those different coupling constants, there are n+1 for n bin prime, there are n+1 for them, so there are this guy plus this guy. These are explicit formulas. And where this is coming from, because these are different orbifolds of the same thing. Because secretly on the boundary, you're gauging different ZMs.
There's no question, but say, once you have this Maxwell theory as a base theory, right?
Yes.
I mean,
Yes.
then, and when you're going to 5-dimensional and consider this boundary, The boundary, the fact that it's kind of associated with the free series, how it shows up in, in the boundary.
Well, it shows in the way that the whole five-dimensional theory is quadratic, so it's also free, right?
Uh-huh.
It's all,
But then you're saying that the unit, the semi-classical factorization is quadratic. You don't know everything.
exactly, that's how we know, that's how I can tell you that one is dual to the other, because it can calculate path integral on the boundary and in the bulk, and they look exactly the same.
I see. But to the extent you do not need semi-classical gravity there, because you see it explicitly.
I don't have semi-classical gravity. Yeah, I don't have semi-classical gravity. I see it explicitly. In this example, I see it explicitly. Yeah, this example I can see it. There is a general proof we have for three-dimensional topological field theories, which doesn't rely on any explicit calculations. A very general proof that you start with any three-dimensional TQFT and you get boundary ensemble with positive coefficients. That then doesn't rely on any explicit calculation.
That's, thank you.
Thank you.